Now let's move to the significance testing for a B weight or a beta weight. And it's basically the same thing. In this example, I'm going to use the beta weight just because the formula is easier to comprehend. And that is located in the middle of the slide. It's the same one we saw on the past slide. And the significance test for beta is really simple. It's a t-test, and on the numerator is just the beta weight itself for whichever predictor, 1, 2, 3, etc. And then on the denominator is the corresponding standard error for that beta. And the standard error for the beta is expanded at the very bottom here. And it has two square root terms, and I'm going to explain what these are here. First of all, we have 1 minus r squared. That's just the basic r squared that we've been learning about. And then this is pretty self-explanatory. This is the total number of cases that you have in your data set. K is the number of predictors. And then we have a term that we haven't seen yet, and that is r1 squared. And basically this just means that we have predictor 1, whichever one's in the subscript, regressed on all the other predictors. So we're going to treat it as the DV and regress it on all the other predictors in the model. And then we're going to get a value for that. And that's akin to the R12 that we had in the prior slide. And it's simply a term that denotes the multicollinearity extent. So the extent to which this particular predictor is overlapping with the other predictors. So that is the term that goes in the denominator of the second square root term down at the bottom. So of course, for the overall t formula to be significant, we need the numerator to be fairly large, but more importantly, we need the standard error to be small, because this can be fairly large, but if there's a large error, then the whole test will not be significant. We won't be able to say with assurance what that value is. Similarly, we could have a smaller beta weight, but if we have a very small standard error, then that might be good because we'd have a small effect that we could detect. So the point is that the denominator is critical here for seeing a significant t for your given slope that you're curious about, and seeing the unique variability attributed by a certain predictor accounting for the others in the model. So big picture, that's what we're doing. We want to see if there's unique variability there. So is there anything else I want to say? So the bottom line is that if we have a large, so you can do this on your own in Excel or whatever, or just take my word for it, even easier, but substitute in large numbers for the multicollinearity versus smaller numbers and see what happens to the entire standard error formula. And what you will find is that the larger this number becomes, the larger the standard error becomes, and the less likely we are going to see significance, because again, the larger the denominator, the smaller the whole fraction is. I hope that makes sense. So substitute in some numbers and start to think about if we have a lot of multicollinearity, what do we expect to find in a t-test for a given predictor? And so unfortunately, if 2 or more predictors are really highly correlated, that is maybe 0.8 absolute value or higher, that means they're redundant with one another, and you can probably drop one or more of them from your study. So I was mentioning in the prior slide that multiple regression is easier if your predictors are not correlated super highly with each other. And that's because it's just easier to tease apart which ones are contributing uniquely to your outcome. And where this matters, I think, is when you're trying to predict somebody's success in a program maybe, or someone's success with a certain counseling technique, and you have available in a database, maybe archival data, a lot of different factors. You have the person's age, and you have socioeconomic status indicators, maybe you have different stressors in their life and things like that. And you're going to find that some of those things correlate very highly with one another. And so you'll be tempted to use some as control variables to understand the unique variability of your program, aside from those other things. The problem with that is that as these predictors become more correlated with each other, it's just harder to tease apart which predictor is causing, or I should say, which predictor is explaining, I should say, the most unique variability. And so that's the issue that we come upon. And I would say that most people don't care about predictors that are correlated 0.5 and below with one another, but once they start getting into the 0.7, 0.8 range, you can start to think about dropping some things from your model because you don't need all of those predictors to explain the DV. So that's just something to think about. And I think that was all I wanted to say about these formulas. Please, for the exam and for just your future knowledge, understand why we want a low standard error, understand why and how multicollinearity affects that standard error, and then if you have a lot of predictors that are very highly correlated, what are some of strategies that you can do moving forward in order to make the best decisions for your client or for your publication or whatever you're using your data for.